So we welcome you to our webinar about managing Wi-Fi challenges in diagnostic use cases. It's slowly going to start and introduce ourselves. I'm Philipp Mumberger. I'm the product manager for VCIs, the Vehicle Communication Interfaces at Softing Automotive Electronics. I'm going to present today together with
Michael von Lesvier. I'm solution architect and for the Softing Automotive Electronics, and also often involved in wireless LAN troubleshooting sessions with various customers.
Today's agenda, we're going to start off with example of use cases for Wi-Fi in diagnostics, and then we're going to proceed with some Wi-Fi basics. Then Michael's going to take over and show some technical challenges and solutions. Therefore, we're going to end with a summary and a Q&A. Just a short warning, we realize that there's way more to explain about this topic. We tried to squeeze everything in there, but we won't be able to cover everything. You can write down your questions in the chat, not in the Q&A feature, please. And we're going to try to answer them at the end, but you are more than welcome to contact us afterwards. So I'm going to show you some use cases for diagnostics via Wi-Fi in the vehicle life cycle. At the beginning of the life cycle, during the engineering phase, you have diagnostic tests, flash programming, measurements, and OBD. And this should all be done in parallel, accessed by multiple engineers, and those users can be in the prototyping workshop, they can be at home and work remote or in their offices, and they still want to access the vehicle. This won't work with a cable, so you need to use a VCI with Wi-Fi. Wi-Fi offers you access for multiple users, it offers you high throughput rate for flashing, and the flexibility you need. Later in the life cycle, during inline production, you have another challenge. You have moving communications partners, the car in the production line. And they constantly move forward, and you have many connections in parallel for all the cars which are currently under production. So you need, once again, do flash programming, read error codes, do variant coding, do some measurements. And therefore, a reliable connection is essential, even in a noisy environment like a factory. And I'm not talking about noisy loud sounds. I'm talking about a lot of EMC being in the factory. Also, a very high throughput is necessary. When you transfer all the flash data, it can be several gigabytes for one car, and then Wi-Fi is exactly offering you this. My last use case presenting is the diagnostics in an after-sales workshop. You can use our workshop tester, TDX. It offers you guided diagnostics, shows you repair procedures, offers flash programming and measurements. And if you have a VCI with a cable, this can be quite challenging. You have your car on a lift, you have a large truck, and still need your computer close to the parts to be repaired close to the vehicle. So using a USB connection is quite uncomfortable. It's for USB 3, you only have 2 meters. That won't be enough for a truck. And in a workshop, there aren't any IT specialists available. So you need something easy to use, and that's Wi-Fi, once again, which is also highly flexible. So we covered the use cases, and let's go on with the Wi-Fi basics. We're gonna give you an overview of the development of Wi-Fi and how it all started, and why we use the frequencies we currently use. For example, at 2.4 gigahertz, the basic frequency for the first frequency for Wi-Fi, water is absorbed by the electromagnetic waves are absorbed by water. We know this from a microwave oven, and this causes a high attenuation. So the military decided in '85 to release this band for public use, and it was the so-called ISM band, the Industrial Science and Medical Band. Some people came up with the idea to use a wireless connection for a Acacia system, and started off with the standard, with the IEEE standard, the 802.11. No letter at this point at the end, not of the standard. It really became successful, commercially successful, when Apple's computer used those wireless standard connection with their airport card. But Apple, being Apple, everything worked fine in their own universe, but not with other devices. So in 1999, the Wi-Fi Alliance was founded to ensure interoperability. They introduced a certification process for devices, and another goal was to speed up the whole standardization process. If you know the IEEE, you have your study group, your task force, your working group, and so on. And the IEEE is also not a national certified body, but a public institute, and it takes a while. So the Wi-Fi Alliance decided to do the work to come together all the companies and speed up the process. And so also already in 1999, you had the standard, you probably all know, the 802.11a with data rates up to 45 Mbits, also already in the 5 gigahertz band. But with the 5 gigahertz band, it also has an issue with water, because water is reflected at those radio waves, and it's was the so-called UNII band, the Unlicensed National Information Infrastructure in the US, but it also was used with weather radar. So it was only usable for Wi-Fi once the DFS, the Dynamic Frequency Selection, and TPC, Transmission Power Control, was introduced in 2003, and it took the EU till 2005 till this band was released. Between 2004 and 2008, some major improvements happened, not in the physical layer, what I told you in the beginning, but concerning security. The WPA2 was introduced. It's more than 20 years ago. Nobody should still be using WPA or WEP. We also had improvements for delay sensitivity, which was important for applications such as video streaming and audio calls, and then also fast roaming was introduced for devices which were moving. And 2009 and 13 new standards were introduced with significantly higher data rates. They were still named .11n and .11ac, but the Wi-Fi Alliance decided in 2018 that those terms are getting way too confusing, especially for consumers, though they introduced the names Wi-Fi 4, 5, 6, and so on. 4 years ago, in 2011, Wi-Fi 6 then finally was introduced. It operates in the old 2.4 gigahertz band, not only as a fallback solution, it introduced a whole new modulation scheme, and also the 5 gigahertz band. There's also Wi-Fi 6E, E for extension. It uses additionally the 6 gigahertz band, which only was released for public use by the national regulation agencies in 2020 for Wi-Fi use. The biggest advantage of Wi-Fi 6 is not the data rate for a single device, it's the increase of total network speed, which makes it more efficient for crowded places with many devices, like stadiums or train stations, and so on. Wi-Fi 7 is using the same bands as Wi-Fi 6, Also focusing on many devices in one cell with slow-moving object. Translated, this means many people in one place which have a maximum of walking speed. The draft of Wi-Fi 7 is already done, but it's not finally released. The final release should happen in this year, and but the Wi-Fi Alliance already has the certification program in place. And the next standard is already on the horizon. It's Wi-Fi 8, planned for 2028. So something about the VLAN Wi-Fi principles. I'm going to start with the bands and channels. I told you about the different bands. Depending on the data rate, you can use a different channel size, at broader or smaller channels. In, for example, in Wi-Fi, in the 5 gigahertz band, you can use 20 megahertz, 40 megahertz, 80 megahertz, or 160 megahertz band channels. In the 6 gigahertz band, the maximum channel size is 320 megahertz, which offers you a transmission rate of 23 gigabit per second. You also have the possibility to combine 2 channels and run them parallel, but this is not possible in the EU since you can't use 2 300 megahertz channels. For the 2.4 gigahertz band, you see a special characteristics. You have overlapping channels. You see that you have 1, 6, and 4 as channels. That is 1, 6, and 11. Sorry. And in the 5 gigahertz band, the channels in between aren't allowed to be used, but in the 2.4 gigahertz band, you have those center frequencies here with overlapping channels. This causes a lot of trouble. Michael is fighting with because when you select the wrong channel or have several devices using different channels, you get your own interferences and noise from a parallel channel using Wi-Fi.
Co-channel interference, then yes.
And it's one thing is the noise. Michael is going to talk more about noise and interference later on.
Yeah.
And there's also the signal strength in Wi-Fi. It's quite important value. We know this symbol here from our cell phone or a computer, but translated it means is the value of the received energy in milliwatt or dBm. When you write it in milliwatts, you see that there is a lot of zeros here. So you use the logarithmic scale in a dBm. It's the value related to 1 milliwatt. And for there are some rules of thumb that you say that up to or down to minus 40 dB, and you have a very good signal. And good values are still from at minus 40 down to minus 72. Then for voice transmission, it's 62. Below minus 71 dBm, it's more or less you can't transmit any useful
yes. If you
data.
If you go to near floor is something like minus 92. Then it gets worse and worse, and the data rates go down, and you have a lot of repetitions and where it sends again. Well, usually fair is from minus 40 to minus 70. Minus 72 is the border for or the boundary for site surveys and so on. Yeah, I can relate it to that. So. Okay, I'll take over. We have in Wi-Fi, we have 2 different modes which are actually dominant. That's the infrastructure mode and the access point mode. The infrastructure mode is usually bigger installation where you have a backbone that goes to other servers, that goes to the internet, and goes to the infrastructure of your company. And it uses probably multiple access points. And what you see here is you have one access point that sends out beacons. Beacons are frames that tell the clients, okay, I'm there, I'm having that SSID, and I'm having these capabilities. There are specific fields in the beacon frame that tells you, okay, I'm supporting these channels, I'm supporting these data rates, and so on. Clients then can associate to the SSID. And what you see here, our VCI, vehicle communication interface, is associated to one of these access points. That's one mode you can operate. You can operate, for instance, the Winning 2000 within a wireless environment in infrastructure mode. Then we have access point mode. I think that is more for smaller installations like workshops and so on. You've seen that with the picture from Philip about the truck. That is where the VCI itself can operate as an access point, and nearly the same as the access point that you see on the left side. And clients like laptops that are conducting tests with the car can then connect. Also, multiple clients can connect to this access point. It spawns then an SSID. It doesn't have that much infrastructure capabilities like a big access point has, like Cisco or Aruba access points or other bigger companies. What you see here is a bigger installation that uses a Wi-Fi controller, a RLAN controller. You see a thing in the backend that is called distribution system. You will find this very often in production sites. The Wi-Fi controller actually has the capability to configure and control multiple access points. It's configured with an SSID profile, and it controls then the access points and also controls something that is called roaming, between where the device moves between different access points. And there's two terms to know here. One is the extended service set. That's actually could be compared to defined by the SSID that you configure. It covers multiple RF cells. Those RF cells are called basic service set. So you see here the APs are sending out RF, and that's actually the basic service set. And if a device moves around, then it can roam from one access point to the other, from one basic service set to the other basic service set. But it's characterized by one SSID. That's called intercontroller roaming. And now we come to various challenges that you will face if you introduce Wi-Fi to your diagnostic solution. That is in essence physical challenges like absorption and reflection. Then RF interference by other devices. Very well known is the leaky microwave ovens, but there's others. And then we have co-channel interference, where actually in the community it's better named as co-channel contention. We'll come to that later. And we have rogue APs that should not be there, sending out RF. Okay, let's go to the absorption. With the absorption, you have typically a brick wall or a damp brick wall, which has a lot of humidity. You have concrete, dry walls, even some windows have some kind of absorption where the signal and these dense materials absorb RF energy as the signal passes through. This yields to a low amplitude. The solution for that is you have to go with a good RF site survey. I will show a slide for the RF site survey as well, where you configure your floor and you configure your walls, including the attenuation of the walls. This kind of RF site survey can help you with a better placement of access points. One more solution is to increase the transmit power, but you're limited there because the regulatory agencies only allow you for certain kind of transmit power. And you can enable a thing that's called management frames that are called request to send and clear to send, specifically for the hidden node problem. But in the very recent development of technology of the access points, it turned out that all these access points have their access points, and also clients have their own algorithm to send out, to start sending out a request to send and clear to send frames. That is because they first have some retries on the frames, and then after some retry phase comes, they start retries with RTS and CTS to secure the frame, to better secure the frame. More details, I will now, if you have questions, answer that. I will answer them if you put them in the chat. Another thing is called reflection. That is typically if you have a smooth and non-absorptive surface, like well, a mirror or a metal, yeah, some kind of like a metal thing in the line of sight between the access point and the client. Such reflections always led to a symptom that's called multipath, where the signal actually takes multiple paths from the access point to the client. There is mitigations or solutions implemented within the access points and the clients with newer standards like 802.11ac and 802.11ax, so Wi-Fi 5 and 6. They allow better signal processing, and they have something that is called beamforming. That can be imagined that frames go around from the access point to the client, and the report is sent by the client, a so-called beamforming report, which allows the access point to better adjust his signal quality with that client. That's called beamforming. Yeah, that is essentially the solutions for reflection. If you have a small installation, you should consider placing the clients in direct sight of the access point. If that is possible, it's possible with smaller installations. Soho routers often have no ceiling mounting. That is very unfortunate. So ceiling mounting often helps with that. And if you're able to put it into the line of sight of the access point, then you're fine. Then you don't have much of a reflection. In bigger installations, it's of course not possible. So you have to live with it, and well, more recent clients are showing better signal processing regarding this one. Okay. I mentioned it already. That's about a site survey. In bigger installations, you should conduct a site survey. Here you see a view of one of the bigger vendors providing tools for site surveys. The first thing that you do when you conduct a site survey is you import the floor plan into the tool. And if you have imported the floor plan into the tool, the next is that you set the materials of your walls. That allows the tool to calculate attenuation values for the walls. So that is the next. And then you have, I think, something like boundary or standard values that you should consider, and that is with this slider. It's labeled with 4. The slider allows you to set, okay, to which dBm value I want to have the signal strength as being good, and when should it start being bad, and so on. You should consider the following boundary values for this. For data transmission, the boundary value is typically -72 dBm. For voice over IP, -67 dBm, and if you have real-time location systems, then -75 dBm. If you have all of the three, then this yields to the value -67 dBm, because that you still need to convey voice over IP with a decent quality. Then you need to add the buffer, and that's typically 3 dBm. Then this yields to -64 dBm, and they set it here to -65 dBm as the border for being good. For the gray areas that you see here, that's around -75 dBm. You need to decide: is there roaming needed? Is there a coverage needed or not? Could be a simple floor where you don't need any coverage, and so on. You need to decide whether you need to place another access point to put more coverage. Okay. Another challenge you will face is RF interference. That is typically caused by microwave ovens in the 2.4 gigahertz band, because the microwave ovens send at 2.45 gigahertz. We've seen and recognized door openers in entrance areas as some cause of RF interference, so that's could be checked then. And we also saw baby phones, and we also saw our repeaters for 5G, LTE, and 4G, but that was suspicious at one site survey, but not really, didn't prove really. But always to be considered, this thing, because that is also a cause of RF interference. RF interference is typically not so easy to detect because you need a spectrum analyzer. Some hints, what's often helping is to ask for specific times. If you have a disturbance, or if you have a disruption, if you have low performance or disconnects at specific times, that could help. For instance, if it's at lunchtime, you probably could came to the idea it might be a leaky microwave oven when everybody eats his lunch meal. There's also in the market continuous monitoring tools that could be installed, typically in bigger installations, and have the capability to archive spectrum analysis, which is a great help in this case. Then you can scroll back in the time and see whether there is some interference being seen at the spectrum analysis. There's in the US, there's one company which does a great work there. That's Seven Signal. In the European area, I don't know, frankly, of a company who's doing that. But those those devices are typically not cheap. Rogue APs are caused by smartphones of employees very often. They spawning an access point because such a hotspot by your iPhone is actually an access point. That can be seen in the dashboard of the controller because the bigger controllers all have a rogue AP detection. And the challenge is then to find the device, respectively the employee having the device. The next thing is about the code channel interference. One thing before we go dive into code channel interference or code channel contention is in Wi-Fi, contention always takes place at the channel. That's to be considered. Contention always takes place. The media access control algorithms work with contention. They have terms like contention window for the backup timer to say, okay, I don't have access right now. I wait with a backup timer for some small time for next checking whether the channel is free. You can compare that to a highway where you have multiple lanes in the highway and the lanes are the channels and there's crowded traffic. You have cars and the cars are the frames and you're trying to squeeze in. So that is something like you could compare a Wi-Fi channel contention with. The topic or the issue or the challenge that occurs with it is that if you have multiple APs sending out on the same channel and actually are close enough to each other to influence each other so that two cells are near enough and are operating on the same channel, then you have contention from both sides, from the clients and from the access points. Typically, this is caused by APs that announce on a different SSID but use the same channel and are close enough, like guest networks, for instance, and bad cell sizing. How big is your cell? That can be controlled via the transmit power. A mitigation for that is a better cell sizing and a channel plan. Channel plan means, okay, I have to segregate mission critical Wi-Fi from not so critical Wi-Fi. Like a guest network is for me not so critical, but the production Wi-Fi would be a critical operation. The next topic is about security. There's two things to be said about security. It consists of two elements. One is the authentication. How I tell Philip that I am I. That's the authentication. And the next thing is then the encryption and ensuring that nobody can read my data that I'm conveying to Philip, that nobody can read it, but he can read it. So that will be encryption. And there's also something like a message integrity codes that actually tell me, okay, the data that I'm conveyed here to Philip is really the data that I'm conveyed. And nobody has tampered with it, or nothing has been. They could also be Wi-Fi tampering bits which flip. It could also be there, then the frame has to be repeated. For the authentication, we have three different authentication protocols. That's open system authentication, shared key authentication, and the extensible authentication protocol. Open system authentication has often been used with internet cafes and airports. You have no encryption. Everyone can log in and everyone can sniff. So be sure about your If you go to an airport, for instance, or internet cafe, be sure to not convey any confidential information. And
or use a VPN.
Or use a VPN, but there's some solutions on the way that have been introduced with WPA 3 in 2018, mainly directed by the Wi-Fi Alliance. That provides a mechanism to encrypt a session without having to authenticate without a password, but this has not been highly adopted yet. So you can't say whether the access point or the client supports WPA 3. And sometimes the older installations in airports still use WPA 2. So should be careful about that. But it provides a solution. Shared key authentication is what you typically have with your home router, with small office and home environments. You have an access point and client share passphrase. That was introduced in 2004 with 802.11i. Yes, nothing more to be said. Often being used in small home and small office and home installations. For bigger installations, you will always find solutions like the extensible authentication protocol. That was actually introduced far back in time, 1998, by the Internet Engineering Task Force with an RFC. But this extensible authentication protocol is just a framework around inner authentications. Those inner authentications are then PAP or TLS, Transport Layer Security, or TTLS, so different authentication methods which are actually conveyed as part of the extensible authentication protocol. So the frames of the extensible authentication protocol are very simple, but the inner authentication, the data that's doing the inner authentication is more elaborated. You have always an authentication server with it, a radius server that provides you with the user credentials and also with the key material to create, for instance, a pairwise master key. Now I come to the second topic, that's the encryption, mainly the encryption and keeping the confidentiality and integrity of the data transferred with a message authentication code. There's three notable technologies. One is a bit outdated, that's the VPA, the Wi-Fi protected access. This has been hacked by teams of the BSI or so, has been hacked. Specifically the temporal key integrity protocol, and is outdated, should not be used, and superseded by WPA 2 and WPA 3. WPA 2 was, as I mentioned, introduced with 802.11i in 2004. It uses advanced encryption standard, a standard for encryption that has been devised with this specification. And it comes in two types. One is WPA 2 Personal and the other is WPA 2 Enterprise. WPA 2 Personal uses the pre-shared key, and WPA 2 Enterprise uses the extensible authentication protocol. See the authentication methods on the previous slide. Then in 2018, they introduced WPA 3 because there was one incident about hacking with very much effort of the WPA 2. You could see that has been in the press. That's the crack vulnerability. Then they introduced, led by Wi-Fi Alliance, the WPA 3. This is characterized by the simultaneous authentication of equals. That means not only the client has to authenticate to the to the AP. Also, the AP has to authenticate to the client. That's the main thing. Also, there's one principle: never convey a key over the wire. Just convey the key material to compute the key over the wireless channel. So that was improved security. They also improved the public Wi-Fi security with this opportunistic wireless encryption. I mentioned this before, that also in internet cafes you could reach an encryption of your data packets. Now we come to something that's called wireless roaming. Wireless roaming refers to the ability of a device to seamlessly move between different access points within the same extended service set with the same wireless network. You may remember a slide I've shown at the beginning that shows you the ESS, the extended service set. It should maintain a continuous connectivity, no interruption. Data should flow while it is conducting a roaming. This is most relevant in production when cars move on a production belt, for instance. But typically it's an intra-controller roaming. You don't have much inter-controller roaming without disturbance. You could see here a roaming event taking place. You have the VLAN controller and the client device moves to the second AP. It was first associated to AP1, then the signal degrades while it was moving. The client device does a background scan. That's very important, so that the client device has a notion of the access points that are in the surrounding. Then it detects that the access point 2 has a better signal quality and better throughput, for instance, and then the client reassociates to access point 2. The buffered data from the access point 1, because there could still be data sitting at access point 1 or even at the controller, the buffered data is then forwarded to the access point 2. With wireless roaming, you need, from the point of view of the client, the client needs to have a view on the access points which are in the surrounding. This is usually done by the client using a thing that's called background scan. It checks for attributes of the access point with signal quality compared to my own signal quality of the current association, with the throughput and with the signal noise ratio, for instance. This allows the client then to make a roaming decision according to a roaming algorithm. There are multiple algorithms implemented in the market. The simplest one is something that's called MINDIF, where you actually calculate a candidate's AP signal strength and build the difference to my current signal strength to calculate a value, a differential value, and then say, okay, if it's above a certain threshold, then I decide to move to the other access point. There's also more complex algorithms that consider not only the signal quality, the dBm values, but also the throughput value or even the signal noise ratio if that is available. There's driver-based algorithms which are not disclosed. And finally, Android, Google does everything the other way. They have a throughput scorer class that makes the decisions with a haystack of parameters. To troubleshoot wireless roaming issues, it is very important to have good logs. Logs of the client and the access point are important to find these issues with roaming. The logs should capture data in a high frequency because a good roaming takes place between 200 and 500 milliseconds. So it's gone. So to see the roaming events, you need to have some kind of a high frequency to log your data to see what's going on. The logs should contain data like the signal level, a roam counter to easily spot roaming events, channel, the TX and RX information, and also the list of scanned access points, of course, because then you can see, okay, what would be the most likely candidate for the next roaming event. It's good to have some software to further evaluate this, but that's, well, you could see here down the picture shows roaming that takes a bit long because you could see the associated state in between. Okay. From the client side, you still have some issues with roaming if the client does not have a background scan, so it cannot make a decision. If it has a very aggressive background scan, which means that it, for instance, has a threshold value of minus 60 dBm and very early starts to scan with a high rate for better access points, or the threshold value is set wrong. You should consider the site survey values also for this setting of the background scan. Roaming still involves a four-way handshake to calculate the encryption keys. This four-way handshake has made trouble in the past and will make trouble in the future. So the four-way handshake may fail and lead to issues. And sometimes, finally to say, sometimes roaming takes simply too long because you have a connection, you have to communicate to the radios, for instance, and so on. So that's also seen that. That's it. Okay.
Thanks.
Hand over.
Thanks, Michael. That's just a short overview. There is much more to say, but not the time to say it all. I'm going to give you a short summary. Just we said that Wi-Fi provides high flexibility in diagnostics and various use cases throughout the whole life cycle. But every use case requires a customized solution. And with all those solutions, we have specific Wi-Fi challenges we can solve by best practices. And we have also, Michael has extended experience, and Softing, the whole company has extended experience with solutions for different production and testing environments. And we're happy and we're there to help and answer way more questions if you have some right now. So, do you have any questions for us? Let's now the opportunity to write them in the chat. Otherwise, Michael is happy to go on
for another hour. Is it okay? No. Okay.
But yeah, and then.
Well, what is just to start it a bit? What do you see here? Well, the yellow line is the TX packets, the packets that have been sent by the client to the access point, and the blue line is the TX retries. So what you see here in the image above is a very congested area where you have lots of contention because you have many retries. So you have almost every packet that needs to be sent out to the distribution system or comes from the distribution system is actually to be retried. So that is very bad. That's a high contention area. Then we conducted the same a few hours later, after 4:30 p.m. And what you can see there is that the retries actually went down pretty much. and you could see that the TX packets are sent and the retries are in a normal way. So you can see that retries are much less than the packets that have been sent. So that means actually that the Wi-Fi system during normal operation working hours is overloaded. And one suspicion that I have here is a bad site survey with a lot of code channel contention. We later found out that with this specific installation, actually the guest network was having many APs in the same channels than the production network. So you could see that really from that's computed from logs from the device. You can see that really from the retries. So I was just to give you a starting point with questions.
So, since there aren't any questions in the chat yet, but perhaps we're going to hand out some information, and if some questions come to mind later on, we are more than happy to answer those questions via mail, or you can contact us via mail, and we'll reach out to you. And thanks for attending our webinar, and hope to talk to you soon.
Yeah, hope to talk to you soon. Goodbye.
Bye.